So the lecture today is going to be about causal discovery. Is, I would say, one of the three most important steps of a causal, the classical pipeline. You see that the field is evolving very fast, so there are many different tasks, right, in causality. But this is where I would say has a lot of developments. This has been going on for like 25 years already. So there are a lot of developments. And the goal of this lecture is going to be very general. So I try to cover, I will give many pointers for you. I try also to cover the basic tools to do causal discovery. But of course, to really going deep on the methods, you have to check the papers and the books. So I will try to give these references for you. You can also, of course, talk to me later. Yeah, so I hope I won't be very fast. Like, I will try to not be very fast in the beginning, so you can start feeling how are the tools, but you can interrupt me at any time if you have questions or if you're not following. Okay. So let's start. So just the outline here, I will try to give the definition and cover what are Bayesian networks. Bayesian networks are basically encoders of conditional independence. So these are just a graphical model that's the base of the causal discovery algorithms. Then I will define Markov equivalence class, which is an important definition for causal discovery. And to understand these equivalences between models, I will use this separation tool. So just a question, who have heard about this separation or know what is this separation? Okay, a lot of people, good. So then I will just discuss the two different types of causal discovery algorithms, first score-based and then constraint-based. But then I will give you more details about one of the algorithms that was, that's the most prominent algorithm when you have no many assumptions under, which is the fast causal inference algorithm. So who have heard about this algorithm before? Okay, that's good. Okay. Then I just discuss about advances. So this is just several pointers explaining what are other works that exist. For example, combining different data sets, observational and interventional. This can come from multiple environments. Also background knowledge, how you model uncertainty. If you impose some parametrical assumptions, you can also go beyond this equivalence class that I will discuss. And then in so cycles and time series data, and then I will discuss some challenges and open problems. So that's the outline. I hope I'll cover everything on time. Let's see. So Dev yesterday discussed a lot of these misleading correlations. So this is just one of those examples. This is taken from this book. It's a very funny book. Like there are several of those examples in this book. And this in particular was just our user on Reddit that posted. And this is showing how the real cause of increasing autism prevalence. So it's just the number of sales and now the individuals that are diagnosed by with autism and sales of organic food, right? So basically you see a very high correlation, but this doesn't mean anything, right? So you cannot claim that organic food is causing autism, although humans tend to do this jump. Another one is, this is even published, it was published in Nature, but as a funny story, like not actually, it's a humorous publication that shows how newborn babies and brooding storks are correlated. So perhaps the old tale is actually right. So this is also taken from this book that storks bring babies. Anyways, this is just an introduction, but the question that I want to cover here is, so correlation doesn't imply causation, right? So everyone heard about this. And why this? So what are how the theory explains this? And the idea is because data is not, you cannot extract from data the real underlying model. So data could be generated from many different models. So there is a problem of no identifiability here. If you just get data, the only information that you can extract from data are these conditional independencies. So you can detect conditional dependencies and independencies. So those are statistical associations. But from those associations, you cannot recover which exactly model generated this data. Even if you try to recover the structure of these models, which is related to the way that you factorize the joint distribution. So you see later, you don't need to understand this right now, but you basically can manipulate the distribution in several ways, leading to different models. And then you see that all these models, they satisfy the conditions of Bayesian networks. We will also see this, which means that they explain perfectly the set of conditional independencies and dependencies that are implied by a data set. So there is this problem of equivalence. So all these models, they are equivalent in the sense of describing or encoding the conditional dependencies that are observed in the data. You cannot rely only on condition dependencies to detect what's the causal direction between these two variables specifically. So between two variables, right, X and Y, which is where we have basically many of these correlations not imply causation, they are always looking at a pair of variables. And from this, you cannot imply which direction, if it's X causing Y or Y causing X, or even this bidirected edge. Dev explained very fast yesterday, but that exists is a third variable that causes both. So there's just a spurious association between them. So it could be like even cause with association. All these models explain exactly the same condition dependencies in the data. So that's correlation doesn't imply causation. And so just a little bit more, just illustrating a little bit more this concept. So from a structural causal model, which was defined also last lecture, but I will define again, you follow the structure. So those are like the just who. So Y is a function of X, and there's also this third variable. So by changing here, what are the functions, what is the distribution of the U variables, and so on, many models encode exactly the same causal diagram. We call this causal diagram when it's induced by a structural causal model. And of course, there are many different, and it encodes different structures. And there is this problem of all of them, even like suppose that there is one, that's the true one, that encodes the true causal diagram, but there is a problem that all of them generates exactly the same data. So when you try to do the reverse engineering here from data, it's almost impossible to get it right. What's the true data generating model? And you can use deep neural networks, for example. You be able to explain really well a distribution that's that we call here observational distribution. And this is the distribution that is sufficient to do predictions. So if you want to make predictions about a reality, this distribution is exactly what you need. So it doesn't matter what's the data generating model, doesn't matter what's the causal diagram. As long as you have this estimation here, you could, then X is a set of predictors. You can predict the value of Y by just running a deep neural network. But the problem is that you don't really know which is the true data generating model. Even if we have something that we call Markovianity in the field, is also associated to, this is equivalent to an assumption that we call causal sufficiency, which means that there's no bidirected edge here, right? So all the associations are explained by the observed variable. So you have no confounding due to unmeasured or unobserved variables. So this causal sufficiency, even in this scenario, you don't know if X causes Y or Y causes X, because you have these two structures that are equivalent. So getting from data what is exactly the true data generating model, even if you have all variables observed in a case of two variables, is impossible unless you add more assumptions, right? So we need to add more assumptions to go back and recover the structure causal model. So that's the lesson here. So even if you run a deep neural network, doesn't matter. It's not going to explain your true causal underlying mechanisms. It's going to be one of these models. It's going to be a very good model for explaining associations or correlations. But if you explain this model that was fit to the data, not necessarily is going to give you the true nature, right? All these models, they explain, they have different causal explanations. So questions related to this. Is this clear? So this is really important because you click when you, so why deep neural networks right now is not able to have causal reasoning is because you don't know if the data that was, so when you fit a deep neural network, for example, even if you have like a very good accuracy for prediction, you're just getting this probability right. So you don't know if it's coming from the model that was fit is actually the true one. So explaining this model doesn't necessarily give you the true nature, right? So we will see how can we do this. So that is this XKCD comic. I really like this, so you can read really fast. And I want to discuss in the end here, so let me just go quickly. So basically it says that there is no evidence, so another huge study found no evidence that cell phones cause cancer. And so that is this graph that basically has almost the same trend. So first you see an increase in the total cancer incidence, and then the number of cell phones increase almost like with a very similar trend. So if you check, the correlation is really high. And the guy here concludes with a funny outcome here. You are not. There are so many problems with that. So because they say that the cell phones cause cancer. And the guy says, just to be safe, until I see more data, I'm going to assume cancer causes cell phone. So who can give me here one explanation of why this is not necessarily true, and what is the problem of this story here? So don't be shy, you can just so first of all, do you think that the guy is right, that cancer causes cell phones? No. Is maybe the other way around? Is it possible to know? Yeah, so that's one thing, right? You don't really know. So, but there is another thing here that the guy says, just to be safe, until I see more data, I'm going to assume cancer causes cell phones. And what do you think? It's really like after waiting data, like maybe waiting more years just for these two variables here, we will be able to see if this relationship is causal or not. No, right? So we just discussed this. But unless we have different approach. So here, if we try to discuss, if you try to discover what is the what's the causal direction, or even if it's a spurious association, just by collecting data, you won't be able to do this. Can any of you tell me some approach that could maybe give you the answer in this scenario? So which type of data we are talking about here? So yeah, in this scenario, they are just collecting passively data. So this is called observational data. Experimental data would be something reasonable to expect to give you the cause of this. But can you do experiments in this case, like cancer incidence? And then I think it's kind of unethical, right? You cannot just do experiments. So I would say that this is like a very interesting scenario that motivates why we are looking for causation without running experiments. So there are several scenarios where they are basically unethical and or expensive and so on. And is it possible to learn causal relations so only or solely from observational data? So that's the question that we want to address by using causal discovery algorithms. Okay. So to understand this, we need a graphical model. So we just need this, the new definition is Bayesian network. Who here have heard about Bayesian networks? I think a lot of people. I'm going to then a little bit quick. But the idea that's very important is that here we are going to use these Bayesian networks to just encode conditional dependencies and independencies. Okay? And it's going to be either a directed acyclic graph, or can be something that we call a cyclic directed mixed graph, because we have now these bidirected edges representing latent confounding. But the idea is the same. It's just representing conditional independencies. So in graphical models, we usually have this graphical kinship notation. So it means that we have family relationships between the nodes. So in this case, X and Y are parents of Z. We have Z as a child of Y, and so on. Let's get a little late. So W is a descendant of X, and I think I need to point here. Yeah, Y is an ancestor of Y, and Y is a known ancestor. So Y is a known ancestor. So ancestrality means that there exists a directed path. So Y is an ancestor of W because there is directed path here connecting Y to W, but Y is a known ancestor of X because there's no directed path. Okay. So just to connect, using this notation for which is a cyclic direct mixed graph, where we have these bidirected edges now. Everything is the same, but we could now have these associations, and we call it spouses, but that's just a name. So a DAG can be, so we will start here under the Markov condition. So let's assume first that there's no bidirected edges, okay? And then it's going to be a DAG. A DAG is a Bayesian network if it represents a joint probability distribution, which means that it has to satisfy this condition. So following this idea of ancestors, of descendants and non-descendants, the variable, every variable in the set V, which are the set of observed variables, has to be independent of every non-descendant given the parents. And under this, if this is being satisfied, then we can just apply the factorization given the parents. So this is always true, right? So the beginning is just the chain rule. So we can factorize as a product of assuming any topological order. But because of this independencies here, we always can simplify and remove every variable that's a non-descendant, because conditioning on the parents, they are independent of the variable. Okay, so we will have this factorization. And this means that the probability satisfying the Markov condition with respect to this graph. And it's important to stress that these orientations here are being ancestor or descendants and so on, has only to satisfy condition independence. So if I give you this graph satisfying, for example, all this, for these 5 variables satisfying this condition, this has no causal semantics. It's really important to stress this. So the only important part here is that I can start with the chain rule, factorize this using the chain rule, and this is going to be simplified by given the parents, which is use the directions now just to know who are the parents, and then we'll have this factorization according to the parents. And yeah, so those are the implied independencies, but sorry, anyways, we will see how to extract these independencies using a tool. But basically, you have a distribution, so a probability distribution. As long as this is satisfying the independencies implied by this distribution, you have a Bayesian network. How can we extend this to a case where we have bidirected edges? So, so it's now ADMG. That's the only difference here. No, sorry, it's one of the difference here, but there's another difference that's something that we call extended parents. And so it's going to have this form. So the joint distribution is going to factorize according to these extended parents. And extended parents has this definition. I'm going to give you the intuition behind it. You can read later. But if this is being satisfied, then we call that P, the probability distribution, satisfying the semi-Markov condition with respect to the graph. So let's see an example, so just to understand what are these extended parents. So the extended parents you basically need are the set of parents of every variable that's in the component that we call confounded component. So it's just all variables that are connected by these bidirected edges. So if we start with E here, the component, this confounded component includes C and E. And then I get all variables, so I just need to assume a topological order, and all variables that are before VI, so let's get E. So topological order, C is before E in the topological order because that is this path here that doesn't allow, that basically imposes that E is after C. So C is before. So I need to get not only every variable in the component, which is C and E, but also the parents of every variable in this component. So A is an extended parent of E. So if you see here, the implied independence is that E is independent of F, F and B. F and B, so E is independent of F and B, given this D, C, and A. So E has as parent D, because it's a true parent, also has C, because it's part of the component, and also A, because it's the parent of this C, which is part of the component. So you need all these parents to condition on. And once you condition on this extended parents, every variable that's not extended parents is going to be independent. Okay, so that is this notion that extends to semi-Markov condition is just a nice way to basically connect to Bayesian networks, to this scenario where we have latent confounded. It's not hard. It's just that in the first time that you see it, it looks very hard. But you need to understand that these Bayesian networks are not only defined for the scenario under causal sufficiency, and this is important for us. So what is Markov equivalence class? I already gave you some intuition. It's basically a class of models that implies the same set of conditional dependencies and independencies. They're going to be all equivalent, I would say statistically, given a data set. So if you have, for example, a joint distribution with just two variables, we saw this example, and then I tell you that in this distribution, X here is dependent of Y, right? So there is no independence between them. And so I use this notation for X not independent of Y. And then I can apply that factorization. So I start here with the chain rule, and then this has to satisfy the parent factorization. So here Y has X as the parent. So here X is a parent of Y. So X is a parent of Y. If I change the way that I factorize this, because I can just take any topological order, right? So I can basically give you as Y. It's not following there, but anyways, these two can be like extended parents or parents, and then I can just describe all the relationships that we had before. So here Y is a parent of X, X can be a parent of Y, depending on the way that you just choose and then apply the chain rule, right? So basically you choose any topological order, and as long as this being satisfying the idea of variables being dependent given the parents, and here we have no independence, basically any graph is satisfying this condition. So that's why correlation doesn't imply causation in this scenario. So all models imply no independence. There's no invariance here. So let's move to a bigger graph, not that big. So just three variables, X, Y, and Z. And then I try to factorize using this idea. So I start here by getting Y, then Z, then X, and then I just apply the chain rule. And I'm using here the independence of X and Y given Z. So in this scenario, I can start by assuming that those are like so this factorization can correspond to this graph where I have no bidirected edge. So X is a parent of Z, Z is a parent of Y, so that's a chain. So I could have this bidirected edge and it still satisfies this property of extended parent. So it's still also equivalent under this factorization. And by changing then the topological order, I can then construct different orientations. So now Z is a parent of X, Y is a parent of Z, and then so on. So this is just the other direction of a chain. And I can even add this bidirected edge, and this is still satisfying these factorization properties that I gave to you. And so on. So basically, I have all possibilities here. I have chain, I have a fork, and you see that I'm not doing anything special. I'm just applying the chain rule and then applying the only independence that I observed in the data. So they are actually equivalent in this sense. So if you look at all these models, they are equivalent, and you see some invariance, although it's hard to see, but it's an invariance that says that Z is never colliding. So there's either one of the directions is with no arrowhead, it's a tail. So you can see that here, there's a tail here, there's a tail here, there's a tail here. So there's always a tail somewhere. So this means it's never colliding. So it is an invariance, which is called non-collider. What else we can see here? So let's now see another example. And this is just X independent of Y. And I would go fast here. And those are the models that you can basically have exactly the same factorization. There's no other way to factorize this. And this is interesting, because since there's only one way of factorizing, there is a special invariance. If you look at all these models, you see now that Z is always colliding, which is called collider here. And if you were in the scenario, I don't have an example here, but imagine that you have no bidirected edge here. If you were in the scenario where causal sufficiency is satisfied, which means that you have no latent confounding, this structure is identifiable, because it's the only possibility is that Z is a collider between X and Y. So you identify a triplet, and you identify that Z is a known cause of X and Y. And if you are under Markovianity, you also identify that X and Y are causes of Z. So that's why those are like gifts from God that Pro was telling in Dev's lecture, because this triplet is giving you this invariance by just observing that X is independent of Y and nothing else. That's the only independence that you observe in the data. So X is dependent of Y given Z, we'll see here. And this is explained only by models where Z is a collider. Is clear this? All right. So that is this tool. So if it's the first time that you are seeing this tool, it is going to be hard, but it's not hard. It's basically you need to get the insight, and I'm going to try to give you this insight for you. So this is a graphical tool that giving a graph that you know that's a Bayesian network, so you know that's representing the joint distribution, you can extract or identify what are the implied conditional dependencies and independencies. So let's see the gifts of God, as we said before. So we have the fork, and there is this very simplistic model here explaining the relationship between obesity, age, and baldness. It's very simplistic, but let's assume that this is actually the model that's behind this variable. So if you observe obesity and baldness, just these two variables, you see a correlation, right? You see that because you see people that are bald, they are probably obese, because basically like with age, which is here, you know that you tend, like you have a higher probability of getting obesity and baldness, especially for, that's why I said simplistic, you need to put gender as well. But anyways, basically, there is no dependence, direct dependence between obesity and baldness. It's just explained by age or sex and so on. And this is explaining this, right? So Z is a confounder. And imagine the situation that you just have this samples, the samples with obesity and baldness, and you see this correlation. But once you observe the age of the person, imagine that the person is a child, it's like the age is like 10, 12. You see that this is not correlated anymore. And that's why we have a dependence here. X and Y are dependent marginally without observing age. But once you observe the value of Z, which is the age, you don't have this dependence anymore. So you have conditional independence. So conditional on Z, you have independence. The same happens with a different structure here, which is a chain where Z is a mediator now. So suppose that I have data for just family history and for family history of diabetes and stroke. Then you observe that X and Y are correlated. But just because diabetes have increased the probability of stroke. But once you observe the value of the person, if the person has or not diabetes, the family history doesn't matter anymore. So it's the point of, it's the same independences, the set of dependencies and independence that we have here. So marginal dependence and conditional independence. Let's try to understand the collider case. So I have this example. It was also in Dev's slides, but I will go. I try to give you the intuition as well. So suppose that I have X and Y again, just a pair of variables, and you observe that they are independent. It's diet X and physical activity Y. In a real scenario, we know that these are not actually independent, but let's suppose that they are. And so you just sample X and Y and you see no correlation there. But then you observe, so suppose you get now a sample of a person that it is obese. Okay, so you observe the value of Z for this person, so, or this group of people. So they are obese. And then you observe as well now that they have like, they are doing a lot of physical activity. They're like athletes. Because of this information, now that you know that they are obese, what can you tell about the diet of these people? Like they are doing a lot of exercise and they are still obese. Something is happening, right? There's echo here. Yeah. Sorry. Yeah, so you observe obesity, and because of this observation, now the information of physical activity helps you to predict the value of diet, right? Because you know now that this person has to have like a very poorly diet. This is the simplest scenario, could be diseases and so on, but let's assume that this is the model that's behind it. So you know that now conditioning on a collider, right? Because we are assuming that this is the true orientations. So conditioning on the collider creates this spurious association between diet and activity and physical activity. And descendants of a collider, they are just proxies of this collider itself. So for example, heart disease in this example is just caused by obesity, right? It's influenced by obesity. And if I observe that the person is now his or she has a heart disease, and it's the same situation, so it's doing a lot of exercise. So you also can guess that this person had. So there is a higher probability of this person having a poor diet, right? So it creates these spurious associations. So those three, actually two cases, because here we have this set of dependencies and independencies. So it's flipped. You know, you have dependence between X and Y and independence conditional Z, and here's flipped. So you can identify, just because these different sets of dependencies, you can identify if it's either a case where there's no collider, Z is a non-collider, or Z is a collider, just because of this. And let's now understand how I extracted this. So for extracting these dependencies and independencies that you saw there, we need to understand what are active and inactive triplets. So the concept is easy. Basically, it's just looking at triplets. Triplets are a set of 3 variables, and I will define as being inactive first. So a triplet is said to be inactive, is always relative to a set of variables, which is going to be the observed variables. And it's going to be inactive if the variable VM, which is the variable in the middle of this triplet, is either a non-collider and is part of the set Z. So those are like examples where conditioning on the variable in the middle is the case of the chain and the fork that I explained to you. If you observe this variable in the middle, then you make this triplet inactive. So those are cases where the variable in the middle are non-collider and they are in the set Z. The other case is like the variable in the middle is a collider, and the collider itself and none of the descendants of this collider is in Z. Because that's, again, the example that I gave to you. When you condition on a collider on a descendant of it, which is just a proxy of this collider, you create association between these two. So you open this flow of information. So once you condition or observe the value of W, you create association between X and Y. So if you don't condition on this, then this is blocked or inactive. So that's a case where is the second condition here to make this triplet inactive. Okay, so there are two cases. Either is non-collider and the variable non-collider is in the set Z, or is a collider and the collider is not in the set Z, or the descents are also not in the set Z. Okay, so now we can define this separation. So this separation is now related to a path, and a path can be more than 3 variables. So a path, and I'm just saying here ADMG because it's just a general, it's just generalizing that DEX, right? Is going to be disseparated or blocked. So a path is going to be blocked by a set of variables Z, if and only if P contains an inactive triplet. So just one triplet being inactive blocks the entire path. It's all you need is blocking one triplet. So that is also a definition exactly about so this separation, right? So a set Z, this separates this, can be sets of variables, X and Y can be sets of variables. If Z blocks every pair between every node in X to every node in Y. So basically you have to block every path connecting information from one side to another. And if they are disseparated, we use almost the same notation as independence. We'll have this G here saying that's a graphical property, right? So let's see an example. Suppose it's just one path, X and Y are just variables, so they're not sets. So to make X disseparated from Y, I need to block this entire path. And I do this by just having at least one inactive triplet. How can I make an inactive triplet? Let's see. Suppose that X is the empty set. I look triplet by triplet. So the first triplet here is a non-collider, right? So to make this, so if I'm not conditioning on B, or like I'm not observing B, or B is not in the set Z, this is flowing, is making the information from X arriving, reaching W, right? So this is open. So this triplet is not in the condition that I explained to make this triplet inactive, so it's active. What about the second one? What do you think? It's the same case where W is a non-collider. So the information from B reads Y. So both triplets, if by set Z is empty, they are open. They are not inactive, or they are active. So this means that X and Y are deconnected. Okay, so that's a no. What about now putting B on this set, in this set? Now you make the first triplet inactive. So that's sufficient. What about W? Again, right? Symmetric. What about both? Doesn't matter. I already blocked one side or the other. I could have redundancy. Now let's see the other example. Now I have 2 triplets and the variables in the middle are all colliders. So as I said, if the collider is not in the set, I make the triplets already inactive. So with the empty set here, what do you think? It's already, what do you think? Is X disseparated from Y given the empty set or not? It is, right? Because both triplets are already inactive. What about conditioning on B? So I'm conditioning on this collider, and conditioning on the collider, I make this triplet active. However, the other triplets is still inactive, so it's fine. Okay, are you following? Yeah. What about W? What do you think? Yeah, right? Symmetric. What about both? No, right? So now I'm opening both. So now I'm not fine. And just another example, just to see if you are paying attention. What about the empty set here? Now I have two paths connecting X and Y. So there is one through this bidirected edge and this edge, and another one here down. I have to block both paths to disseparate X from Y. Who can tell me what set here disseparates both? You. You can tell. He's telling this the empty set. So the empty set makes this triplet inactive. What about the other? Is it still active? So it doesn't work. Do you all agree? Yeah. What about B? Doesn't work as well because now you open this collider and then this path is open. What about W? It works? So W is a descendant of B, and B is a collider on this path. So once I condition on W, I block this path here between X, B, W, and Y, but I open this other path because conditioning on descendants of collider also open the collider, which makes then this path active. So it doesn't work. What about B and W? Doesn't work. So this is a case where we call inducing path, where although there is no edge between X and Y, this graph is representing no independence between X and Y, given no independence. There's no independence set to make X and Y independent. Okay, so this can happen. It's from directed graph. So this definition was created when the field started only with DEGs. DEGs are directed acyclic graphs. Then this was defined by just extending the notion of separation, which also has, we have definitions for separation when you have undirected graphs, other chain graphs, you have many other types of graphs, the probabilistic graphical models. This is the extension of separation for directed acyclic graphs. And now we should use D-separation, although we are working on ADMGs. Okay. All right, so now you are an expert in causality because this is everything you need. It's funny, but everything builds on up on this tool. And let's and this is important, right? So this is just a connection that ever this separation in the graph, it's implying or showing that this independence in the distribution is being coded, right? So there is this implication here. So a graph, if it's a Bayesian network, once you have a separation, it's because it's encoding or implying that there exists this independence in the joint distribution. Yeah. So one thing that helps a lot once you have these graphical models is to understand which conditional dependencies and independencies are implied by the true underlying model. So we saw as well in the lecture the last lecture with Dev this Markov blanket, and he didn't define because he was just inspiring you about the tools. But I will define now. So Markov blanket is the set of variables that there is a theorem that I'm not telling you here, but there is a theorem that tells you that the Markov blanket is the best or is the optimal set of variables for making predictions. because it's the set of variables that are all correlated or dependent of one variable. So in this case, it's like always a blanket for a variable v. So a Markov blanket for one particular variable z is the set of all variables that are correlated with v in this greedy way I will explain. So suppose that I have this variable here, and I start with all the neighbors, because neighbors includes parents and children. And they are correlated because they are directly connected. So there's no question here. But you see that once I condition on the neighbors, I open these colliders here. So opening this collider, I create association also with the parents of the children. So the parents of the children is also part of the Markov blanket. And these all gray nodes, if you are trying to make a prediction, if you have those variables, you are going to you can make better prediction by including those variables in your model. So all those help to get what are so the probability of V is different once you condition or observe these variables, right? So they are dependent. So that's just definition of probability of dependence. So those variables are going to help to predict the value of V. When you extend this for semi-Markovian models, you need this notion of district, but you see here the definition, you can check later, but the idea is exactly the same. You get the neighbors. Once you condition on colliders, you add another variable to the blanket because you create these associations. And there are several, that is a special case here. So imagine, for example, that all these variables are connected just by bidirected edges. By conditioning on them, you can extend this region of influence, and then the parent of this last variable here is going to be also part of the blanket of V. And you can see through this graph that variables that are completely unrelated, causally unrelated to V, can be part of a model that's just helping you to predict for a predictive task, right? So getting variables that are relevant for prediction, for example, doesn't give you any hint about if this variable is causal or not. It's just like they are associated somehow through, for example, bidirected edges or just neighbors and so on. So that's why you understand why even when you fit a model that has a very high accuracy, those variables not necessarily are causally related. And worse, like the causes are just a subset of it. So in this case, I just have one. You can have undirected causes that once you condition a directed cause, they don't help anymore. But there's only one cause here. So if you just have like a model doing prediction using just the cause, this is not going to give you the best predictive power, right? You need other variables because they are just giving more information about these variables. All right. Questions related to this? All right. So now let's move to causal discovery. So we want this causal, this is a task where we are going to learn these invariances that you saw, right? So that's all we can do. So we cannot learn from a pair of variables what's the direction of one to another, but we can try to basically list all the models in this equivalence class, see what's invariant, and I don't need to know what's the true graph, the true causal diagram, because since this property is invariant, I'm sure that this graph is going to have. That's the idea behind causal discovery, is learning invariances. So we are going to learn a representation of the Markov equivalence class. Okay. They've also explained the number of graphical models that between, like, for a specific number of variables, it's a huge space. So the space of the X grows super exponentially with the number of n. So with the number of variables. So this is the recurrence formula. Basically, I have here a table. You can see that if you wanted to just do enumeration, you can start maybe with 2 variables, 3 variables. I would say 4 variables. You can take like a whole day, maybe a week if you're a bit more lazy, to list all of them. But I don't know, I'm lazy. I would never do this and start listing. And then you see with 8 variables, it's to the power of 13. I would never do this, right? So computationally, it's infeasible, even like for DAGs. And DAGs here, remember, there's no bidirected edge. even for DAGs, it's really hard to do causal discovery by doing enumeration. When you move to the space of ADMGs, we have even a larger space. Now it's the number of DAGs now multiplied by the possibilities of bidirected adds you can add. So you see that now with 3 variables, I'm already like, I don't know, I cannot do even with 3 variables. Imagine for 4, 5, and to the power of 21 for 8 variables. So scalability in causal discovery is a very huge problem. Because of this, people are like trying, so there are search algorithms that are trying to use optimization approach to search this more efficiently, the space of DAGs. Sometimes they impose assumptions, like let's suppose sparsity, sparsity. So it's a NP hard, so there's nothing we can do, right? So we have to deal with this. All right, so that's a lesson. Causal discovery is not feasible through naive enumeration. So how can we do this? So to learn the Markov equivalence class, we first need to remember here that there is identifiability problem. And the identifiability, it's a problem when you have no assumptions. So let's start just using conditional dependencies and independencies from the data. So this I trust, because once you if you increase the sample size you go to the limit, then you have like statistics supporting us to have asymptotic results. So let's start in this setting. So I call it non-parametric because I don't want to make parametric assumptions or distributional assumptions. I don't want to say that's linear or non-linear or or Gaussian or whatever. I just want to say that the only thing that I know is that I have a very good condition independence test that's going to tell me which pairs of variables are dependent or independent of each other, given some others. So this is so in the setting where I'm just having observational data, I'm not using anything else here. No interventional data, no knowledge, no other type of data. So in this scenario, causal discovery can only learn a representation of the Markov equivalence class. This is what we understood from the previous slides. And we have 2 types of algorithms, either score-based or constraint-based. A huge part of the literature works under the assumption of causal sufficiency because it's easier, it's scale, and a lot of things that are very good in this scenario. You can tell me, oh, it's very unrealistic. Maybe, but some other scenarios you can do it. Maybe you observed a lot of variables. I think IMEDs, maybe it's some scenarios where sufficiency maybe is satisfied. But there are other algorithms that are not assuming this. And even if you have latent confounding, you have a way to learn the equivalence class. Okay. No latent confounding, so no bidirected edges. Okay. So all the associations are explained by the observed variables. And yeah, that's the assumptions right there. So assumption that all confounding variables have been observed. So although strong, it has been widely employed to simplify causal discovery inferences. So the field is kind of in these 2 directions. There are other assumptions that you can make to go beyond the equivalence class. We will see some other works doing this direction as well. So score-based, the strategy is just having a search algorithm, can be a grid algorithm, to find the most probable causal structure. And you assume that you have a goodness of fit score. Can be like Bayesian information criterion, BIC, if it's all your variables are Gaussian. Can be BDOI, BDU, I don't know how to pronounce this, like for multinomial variables. And as long as you have a score, people are working on developing more general scores also for non-sufficient scenarios and mixed variables and so on. But if you are under causal sufficiency, then you have this algorithm. This was in 2003, is a classical algorithm. And there is the extension of this for like there's a better runtime because it's using parallelization. So it's the fast GES, grid equivalent search. So these are like the beginning of the causal discovery. And now other algorithms have been developed to account for latent confounding. And I would say that there are a few. I want to list them. So GSMAG is a work from 2016 from these authors. They learn. So you see this MAG here. This is maximal ancestor graph. I'm not going to define it this lecture because it would be very heavy. But that is a transition. Like when you work under latent confounding, you need to map a class of ADMGs to an object that's called maximal ancestor graph. So maximal ancestor graph is already a class, an equivalence class of ADMGs. But in the end, you have a higher level of equivalence class, which is going to be the partial ancestor graph that you define. But you could basically go to the level of the maximal ancestor graphs and do this grid search. And this is one of the works that's doing this. Most of these grid algorithms, they don't have they don't prove that they find a global optimal. They can always be stuck in a local optimal. And this other algorithm here in 2021, they use dynamic programming and branching bound. That they prove that you can actually find a global optimal maximal ancestor graph. There's this differential discovery approach that now it's doing the search over the space of ADMGs using a continuous optimization process problem. It adds a little bit like some assumptions regarding to smoothness, so you can make this as an optimization problem. But they are all under the assumption that you have you are working with the BIC. They only work for Gaussian variables, right? So they assume linear Gaussian models. There is this new one in 2000. Oh, this should be 23. It's not 13, 23. The neural ADMG learning, it extends the discovery algorithm, but they don't try to find ancestor graphs. They make this assumption that your ADMG is both free, which means that if you have a pair of variables, either you have a directed edge or a bidirected edge. You cannot have both. Can be like a strong assumption, but in this scenario, they extend to a non-linear structural causal model with additive noise. So it's using other type of assumptions to do this search efficiently. So going now to the other paradigm with the paradigm that's basically constraint-based. So constraint-based is because you're using these condition independence tests instead of a score. And the strategy now is going to use all these observed condition independencies to create some type of logic, or like some rule. You can apply some rules to satisfy the logic behind conditional dependencies and independence in Bayesian networks. So under causal sufficiency, this is started with the IC and inductive causation algorithm by Verma Pro in 1990. So it's very old. The PC came right after. It's like an improvement in comparison with the IC, but in PC, it's still used up to date. Like everyone, it's like if you are under causal sufficiency, they use this a lot. Basically, they learned an adjacency structure, like it's a skeleton. It's just an undirected version of the graph. And then you use a set of rules that tries to, which plays like the collider, when you identify the collider through this idea that you have like a very specific list of conditional dependencies and independencies, you can apply these rules sequentially, and then you learn at other orientations. I will give an example later, not of the PC, but of the FCI, which is an extension of PC, as you see next slide. And if you want to read about this, the original algorithms, and this is still, I would say, a very nice book, like it's old, but it's where you would have like a very nice introduction for the PC algorithm, FCI algorithm, and so on. So I recommend this book, Causation, Prediction, and Search. Then accounting for latent confounding, we have now a lot of algorithms. basically, we start with the FCI. So the FCI was developed in 1995. And in 2008, Gigi Zhang proved the completeness of this algorithm. So it developed like a set of 11 rules. And then it developed, now I would say that's the most prominent algorithm today. Of course, we have several variants of the FCI, including all this here, anytime FCI, conservative FCI, because they are trying to improve robustness, scalability. But the idea is exactly the same. Like it's basically the same algorithm with a very small difference. Another interesting approach that has been developed also by using the idea that the dependencies they create this logical characterization of the Markov equivalence class. You can basically list all these logical statements and then solve this problem using answer set programming. And this was first introduced by Hittinen in 2014, but now we have other algorithms. For example, this ancestor causal inference. They use this approach as well and learn a representation of ancestral graphs, which is this object that I told you that basically goes from the ADMG to this ancestor graph, and then we have a representation of all these modules in the end. Okay, so let's go a little bit more in detail about one of the algorithms, that is the constraint-based algorithms in general. So this is the same illustration as before. So you have a data, you really don't know what's the model that generated this data, but you can test using a condition dependence test, what are the conditional dependencies and independencies there. And this is the case of the collider, right? So you have a marginal independencies plus everything dependent. And you can basically have this list, but I don't want to do enumeration, but I can apply this causal discovery algorithms, for example, the FCI. And in the end, we will have something that has this look here. And you can see that everything that's not a circle, like this arrowhead, is an invariance. So if I have something that's not a circle, it means that in any model inside of this class, this is present. So it's true in the true causal diagram. In this case here, the arrowhead means no ancestrality. So it means that Z is a no ancestor of X, and Z is also a no ancestor of Y, because there's no directed path there. So let me show you a little bit more about the FCI algorithm. So let's assume that, so this you don't know, right? So this is the unknown reality. So imagine that this is the true causal diagram, I don't know, but this graph is representing these conditional dependencies and independencies in the data. This is just the independencies, but everything that has an edge has a dependence. You just check by this separation, what are the implied dependencies there. But I don't know any of this, right? I start then with a complete graph. A complete graph is the least informative graph you can have, because edges don't necessarily mean that there is a dependence right now. It's just that I haven't tested. But if you, when I look at these graphs, I like to think about parameterization of the space, because you could even have like an edge that has zero effect. So they are there, but they don't mean anything. And basically, we start with the least informative graph. You don't interpret, you don't connect edges right now with dependencies. But then I can have a list of these independencies in the data. And here comes one assumption that I want to stress that may be one of the, I would say, the major limitation that's behind of this algorithm, that's called faithfulness, because it's assuming that your condition dependence test is giving you the right decisions. It's like it's really independent, it's really dependent, so on. Of course, this is a statistical problem. We have like, to get this correctly, you just need a very large sample size. You need like condition dependency tests that are making assumptions that's fit into your scenario. So it's just throwing under the rug here a little bit of the assumptions, but this has been one of the topics of research right now, how to make these algorithms more robust under unfaithfulness. But that's the how it started. So under faithfulness, we assume that this is actually implied by the true model. And then we start removing the edges between everything that was found independent. So between X and W here, doesn't matter what's the conditioning set. Then I remove the edge. The same for X and Y. Doesn't matter what's the conditioning set, I remove the edge between X and Y. Then there is the set of 11 rules, because there's the rule 0 before everything here that's identifying the colliders. But then you apply these other 10 rules that was developed by Spirits in the beginning and then extended by Gigi Zhang. But with these rules, you have a final representation of the equivalence class, and it is complete, which means that if it's a circle here, it means that this data set cannot give you the information about what is the relationship here, which means that the graph where you add an arrowhead here or the graph where you have a tail here, they are both equivalent, or they both represent exactly the same set of observed dependencies and independencies. So, however, there are invariances. So here was the collider case. You can learn other things. So here in this case, I have this black arrow, which means that, and this is an ancestral graph. This is something that I have to stress, because these edges, they don't necessarily mean direct edges in the causal diagram. They just mean that exists a directed path going from W to Y, which means that in the sense of causality, it's okay, because if you intervene on this variable, you see a change on the variable Y. So, right? So it doesn't matter if this is direct or not. And however, this green edge here, we have this V for visibility. It tells there is another condition that allows us to know if this edge is not only a directed path or showing ancestrality, but it's also unconfounded. And the fact of being unconfounded means that later, and we will see tomorrow, we will see that we can even identify the effect size of this as the causal effect. So this is a required, not a sufficient condition, but only those edges that are unconfounded can be maybe have the effect identifiable. But that's the general idea. So you see here that this peg, there is an extension of the D separation, which is called M separation for mixed graphs, where it's very similar. You see in Gigi Zhang, also in one of the references that I will tell you here, you see the definition there, but it's basically the same idea. Like you can condition on definite non-colliders, and then you have like blocked triplets and so on. Okay, so you see here we have some different types of edges. So this circle, they are just uncertainty in the sense that I cannot, because it's equivalence class, but arrowheads, they mean no ancestrality. So B is a no ancestor of A. Tail is an ancestor, so definite ancestor relationship. If you have a bidirected edge, it's just that there's no causation in any direction. So it has to be some other variable, a latent variable that is causing both. And you can even have undirected edges, because if you are in the scenario where you have selection bias, which means that your sample was collected just biasing in one of the categories of your variable, for example, you can even detect it through these algorithms. Yeah, so here's just interpretation. So condition independence tests, this is a building block, right? So I need this condition independence tests to apply the algorithm, any constraint-based algorithm. We have several, and many people are still using this. It's like a very, like it was the first condition dependence test. It's assuming that every variable in your samples, in your data sets is Gaussian. Of course, not necessarily you are in this condition. So some people extended, for example, to have kernel basic non-parametric tests where you have no Gaussianity involved. You can apply this for any type of functions. This is implicitly assuming linearity. So this is working for any functions. So there's no free lunch, right? So if you have like very general tests, you need larger sample sizes to detect it correctly. So even though like that exists this very general tests, a lot of people are still using the Gaussian version that's a partial correlation test, and also this one that's based in linear regressions, because if your sample is not necessarily big, and which I mean, and for big, I mean, it's like you don't have like thousands and thousands of samples. Like if you are like in the 1,000, I think it's kind of hard to detect correctly our conditional dependencies and independencies. So people are still using some assumptions. That's why I said under the hood, there's still like some assumptions behind, but increasing the sample size, you could relax this, right? And you can develop your own, like this is like one of my papers. I developed like one condition dependence test. When you have like correlations among your observations, you can just develop your own. Like this is even today is a very active research topic, because doing performing condition dependencies is too hard. So I want to just list here, if you have like if you run the algorithm and you have this output, that was the example that I had before, you need to know as well that is a characterization that allows you to enumerate the graphs that are inside of this. So if you want to do this exercise, you need to know more about this characterization. But you would, for example, basically replace these circles to arrowheads or tails. So you can see that can be like just directed edges or can be bidirected edges. This W here is a non-collider. So being a non-collider is an invariance, which means that you never have W as a collider, but you can see that the non-visible edge can be a bidirected edge. That's what I thought, as I told you, as long as there is a directed path connecting W to Y as an ancestor of Y. So enumerating these objects inside of a peg, it's not trivial. You need this characterization, but this gives you a lot of information, because it gives you who is ancestor or cause of each other, who you can just don't know, and even this part of visibility. So yeah, this was the true graph that we started with, like in the example. So it is one of the class, one of the members of the class. So here are just a bunch of other examples. So for example, this is the collider. So this is the graph related to the class, the equivalence class that includes the collider. Yeah, that's fine. So the collider there is part of this equivalence class. Oh, it's back. So this is the fork. So the fork is going to be represented like this. So you see that that is inside of the characterization. This is one case where we know that it's a definite non-collider. So that is an invariance there, even if you don't see any non-circles. And you have a lot of them. As an example, you see the one here, you can learn that X is a cause and a confounded cause of Y. This is just a spurious association between Z and W, and that's our example. Questions related to this? Yeah. How much time I have? 20 minutes. So I plan to go like step by step as well in the algorithm. So I go just very quickly on this. If you have questions, just interrupt me. I just wanted to illustrate what are those rules, because they are just very abstract right now. So the skeleton, as I told you, so imagine that this is the unknown graph, right? So we don't know it, but we start the skeleton by doing what I told you. So you start with the complete graph, and then with a lot of these condition dependencies that I can do. That is a smart way of computing these condition dependence tests. The naive way would just like go all possible condition dependency sets that you can have, but the algorithm is smarter than this. So, but once you find the first independence, you can stop. Because once you find one independence, you can remove. So for example, if you have these independencies, you can remove the red edges here, and then you can remove the edges from the graph. Then there are a set of rules, and these rules, you not necessarily need to follow the order of these rules. You can apply these rules as long as they are applicable, and you continue trying to apply until they cannot be applied anymore. So the rule 0 is one of the cases where you learn the collider. So you saw this, how to do it. So if the variable in the middle, if there is a triplet, the triplet is not V1 and V3 are not adjacent, which means there's no edge between V1 and V3, but they are connected. But V2 is not part of the conditioning set. So this means that V2 has to be a collider, because otherwise, if you were conditioning on the collider, you would be opening this path and they wouldn't be independent. So you see, the proof of these rules are very simple. It's just like finding contradictions. And you'll find this collider by this idea that I told you. And then in this example, you see that V2 here is not part of the conditioning set. So V1 and V3 are independent just given V4. You can see in the true underlying graph here through the separation that you only need to block this path, but this other path is here, you don't need to block. So the independence between V1 and V3 under faithfulness is just given V4. So you would observe this through a test, but you would see just this dependence is given V2, for example. So this makes V2 as a collider. It's the same as V5 here, right? So you apply. There are other rules. So for example, the rule 3 here, basically if you find this structure where you already found a collider, and now V4 here has like a circle and is connecting this sense, you for sure know that this is an arrowhead. So the logic between for this is just that if it was in the other direction, right? So this is an arrowhead, because if it was a tail, then the V4 would be a descendant of a collider. And being a descendant of a collider means that it wouldn't be possible to be in the conditioning set. So again, very simple logical reasoning. And you can detect these invariances. And again, you can for sure know that there is an arrowhead here. And you can go over and over. So there's this rule 1 that's one that's even related to visibility, because if you have already an arrowhead here from the previous steps, you for sure know that this has to be a tail and an arrowhead. Because if not, like imagine that this is also an arrowhead here. This means that V2, when I condition on V2, I open this, and then you wouldn't find this independence. So for sure, if V2 is separated in this triplet, if V1 and V3 are separated, not adjacent, and V2 has an arrowhead, for sure there's not another arrowhead here. And this gives you the idea, again, of unconfoundedness, because if it was a bidirected edge here, is the same reasoning. So you apply the rules and, oh, sorry, anyways, but you apply the rules and then you get, it was here, this tail here. So there are other rules. So this is something that we call discriminating path. It's very complicated, but once you find this structure here, you know that for sure the edge between X and Y has to be like this. It's just an extension of the collider. You need to condition on Z1 and Z2, but once you condition on both, because you need to block these first two paths, once you condition on these two, the X either is part or not of the conditioning set. If it is part, then it's because it's definitely not a collider. And if it's not part, it is a collider. So in this case here, it was part. So I have this tail here going from V3 and V5. So I'm just continue doing this. So there is another discriminating path that allows you to add the tail on V1. And that's the final graph in the end. You can check later. I have a list of all the rules, even in the slides. You can check that you cannot apply any of the other rules. You can go back to 0, 1, 2, 3, 4. You can even go up to 10. And there's never a structure that fits to the condition of applying a rule. So which means that this is your final graph. And it's a complete algorithm. This means that you cannot do better. This is the best representation you can get. It is the representation of the Markov equivalence class. So yeah, so that's the final peg. You can check even that that's a visible edge, but you can check even that the true underlying graph has exactly the same implied condition dependencies. So it's really representing all modules of the equivalence class. So here is the set of all rules. You check later. I won't go over them. In Gigi Zhang's paper, there is the proofs. There are the proofs. They are very simple, are really nice to understand, but you can just go and check them. Yeah, there's a set of 10 rules, so I'm skipping, but I wanted them here so you can take a look later. And you can even try at home to get this back. Okay, you apply basically these rules and plus the rule 9, it's an extra rule here. And you see that it's going to apply, it's going to imply exactly the same set of independencies. All right, so now, there is another thing that if you are interested in implementations, there are a lot of packages available both in R and in Python. So you can use your favorite language here. So those, I confess I use more R than Python because I do more things than just discovery. And most of the tools are available in R. So, but there's a huge, I tried later to do to add a Google Drive, but I was unable to do it because of access. I asked the organizers to give me access again, but you add there. I put on Discord these slides. And as I said, like I use a lot R, but people have they are doing a lot of effort in nowadays to have like packages in Python. So do discovery is part of the do Y package that Dev explained last time. So Causal Learner, he also told about this. So yeah, so I would say that I still work on R, but I should be moving soon to Python because it scales better, right? But it's still a lot of packages are in R. And yeah, so I want also to give you some pointers about what's happening out there. So this is just, I cannot forget about the hybrid approach, they are classical approach. So that just combined is core and constraint strategies. So this is still, it's not that old, 2018, but it extends the GSMAG, it's one of these core-based algorithms, by using these constraint-based phases to reduce the space of structures. So the GFCI was also very popular in the past because it's combining the FCI with the FGES. And there are people also working on parametric assumptions. So depending on your setting, maybe it's interesting to do this. So it's really interesting. For example, if you assume that the functions are all linear and your errors are all you can have at least at most one Gaussian error, but all of others have to be non-Gaussian. And you are in a cyclic model. Shimizu in 2006, he proved under causal sufficiency, so a lot of assumptions here, right? Assumptions of sufficiency, linearity, non-Gaussianity. You can have the true causal model, the true causal graph, not model, the true causal graph. So you have identifiability there. Some other researchers, they proved as well that for non-linear functions, but then you have an additive noise. So there is a function of the variables plus a noise. Then you can also have identifiability under causal sufficiency, right? Because in these distributions, you have some asymmetries in the distribution. So you can basically plot the both directions, and you can see there that the one direction is more probable than the other. But you need those assumptions. So how can you go beyond the equivalence class? Many times we are not just in the scenario where only observational data is available. Sometimes you have something more. And people are trying to integrate this data set. So one of the things that's really interesting is how to combine observational with interventional data set. So I would say that this was one of the first to do this in the scenario. I'm focusing now only on the scenario of unobserved confounding, because under causal sufficiency, people are doing this even way before, but when you have latent confounding, things get harder, especially because you have to prove what this means in terms of equivalence class. It's no longer a Markov equivalence class, it's another equivalence class, so you have to characterize the class that you're doing this. And so this paper, Haber and others, they basically show how to do with soft intervention. Software is just an intervention that's it's just increasing the probability of doing an intervention, not necessarily doing you don't have 100% of certainty that this intervention is happening. Recently in 2023, they also allowed you to have interventional data coming from multiple data sets. So you not only learn where and how, and one important part here, you don't necessarily need to know which variable received the intervention, the targets. And they extended this work and the scenario where you have multiple environments. So you learn as well distributional changes. So if you have like data coming from from different environments, these environments can have like different distributions because you have like, for example, different age distributions and so on. And the algorithm can detect this. So this is just one example showing how you have to extend the equivalence class. So you have now this square nodes pointing where there is a distributional change because of the different environments. These F nodes are representing where the intervention is probably occurring and so on. And you have like a peg that they call, in this paper, they call psi peg. This is, they call S peg. They're putting Greek letters everywhere. So yeah, it's just a new representation of a class, equivalence class. Another one that's interesting is like adding expert knowledge, prior knowledge. So they have, it's a very hard problem to show completeness. So no one actually showed completeness given prior knowledge yet. But in some specific scenarios, they prove completeness. So here, for example, they have completeness with local background knowledge. There's like, you need to know everything that's happening in a very local neighborhood. Maybe a strong assumption or not. So very recently, it was by Perkovich, by Van, these authors, they showed that they just conjecture that's complete, but they extended the FCI to actually add background knowledge. And there are extra rules there. I also worked on this, so I have this algorithm for like adding a human in the loop. So you have like optimal experimental design involved to ask the human what exactly is the direction of one particular edge that's going to minimize the cross entropy. And you can even have noise in this feedback. So basically, it's a Bayesian approach because you learn the distribution of these ancestor graphs, and you allow this interaction with the human in an optimal way. Also, you can continue doing some parametric assumptions. So in linear models, you can do more than just going inside of the Markov equivalence class. So in 2014, there was this partial LinGAN that tried to extend the LinGAN that I told you to have like latent confounders. And they proved that you have like this causal ordering. So you are learning just the order. However, recently, Wang and Durton, they proved that this algorithm specifically was complete for learning maximal ancestor graphs. So you can learn under linear models a class that's not the Markov equivalence class using this approach here. And they did something more that's, I think I have here a note that I don't remember exactly. I think they treated the case of a Beaufort graph as well. So they not only proved that this is complete, but they did some extension to more particular graphs. And there's also this paper here that was published in last year, also going beyond by using additive noise models. So they combine the FCI with this new criterion that's causal direction criterion that it's not assuming sufficiency, but it's assuming something that's called independent causal mechanisms. It's kind of related, but it's a little bit more relaxed. And some people as well are working on extending these algorithms to deal with cycles, because as Dev told you, in the beginning, they started defining the structural causal models as being acyclic, right, recursive models. However, recently people understood that you can deal with some cycles, some feedback loop there. And these authors, they show that even the FCI, the one that I showed you, it's capturing some graphs inside of the equivalence class that has cycles. So they extended the separation of our sigma separation. So there are several extensions where you deal that you can capture independencies that are coming from cyclic models. So this is a very nice paper, and they establish now what are the equivalence classes under this scenario where you have cycles. Time series data, like once you have time series data, you have several challenges, especially regarding to recall, because the time, if you have like a long gap, a long lag in the time series, you need to condition on many variables. So this can reduce your statistical power. So this paper here is showing how to not only add the knowledge that the past, the future and the present cannot cause the past, but also they deal with some heuristics to help to have a higher recall. And I guess, yes, that's all. How much? Almost done. So that's on time. So I want to discuss some current challenges in my vision. Of course, many other researchers probably have other challenges. Those I would say that the challenge that I am even researching on them. So the first one is robustness. I've been working a lot on this because if you have unfaithfulness, like your data is, or your tests are getting a wrong conditional independence test, or like just an independence giving a wrong conditioning set, the FCI can be very wrong in getting a very wrong output. So I'm working on making the algorithm robust and giving different scores, as I told you before, like non-parametric scores to give some certain, some notion of uncertainty. Scalability, so it's an NP hard problem, so you cannot do much. However, you can construct adaptive approach because, as I said, you can have latent variables, you can have latent confounding, so you don't need all the variables.